Welcome everyone to the second day of the EC'24 tutorials. We're going to have today Evie Mija who is currently a postdoc at Harvard University and will soon be joining USC as an assistant professor, and Nisarg Shah, who is an associate professor at the University of Toronto and the research lead at the Schwartz Reisman Institute, lead the Fairness in AI and Machine Learning via Social Choice tutorial. So just a little bit of housekeeping, send clarifying questions on the chat. Either Nisarg or Evie will be handling that, and then there will be time for questions at the end, and the questions that are big enough, they will pass them on to the speaker. So thank you so much, Evie and Nisarg, for organizing this. I'm very much looking forward to it.
Thanks, Laura. All right, hi everyone. It's our pleasure to be here, and we are very excited to kind of bring this tutorial to you. This is the very first time that we have prepared and we are delivering this tutorial. So please excuse us if there are kind of some hiccups along the way. Okay, so since Laura has already introduced us, let me just go ahead and dive into kind of the tutorial. So before I do that, a few disclaimers. One is that the high-level idea of this tutorial is on focusing how to apply various ideas of fairness that have originated in social choice theory to the modern decision-making applications in AI and machine learning. And so because of that, we are going to keep the tutorial focused on kind of the more conceptual applications. So we are going to focus a lot on how you can actually model different AI/machine learning applications in the social choice framework, where you can apply some of the fairness definitions coming from social choice meaningfully in that particular application. So we are going to focus a lot on the modeling portion. We are not going to focus as much on the results, and we are not going to focus in particular, we are not going to include any proofs in this tutorial. So kind of those of you who are worried a little bit, you can sit back and relax. That said, a lot of the papers that we are covering, they do have very interesting theoretical and empirical results. So if you're interested in that, please check out those papers, and we'll have the references at the end of the whole tutorial. All right, and because we are going to cover many different settings, it's going to work a little bit different than some of the other tutorials that focus on one setting and then kind of go into depth in that setting. Here, because we have to cover so many different settings, we will not be able to always define all the settings super formally. So sometimes we'll define kind of the main aspects of those settings mathematically, and then we'll just convey the intuition of how you can take that setting and then map some of the social choice fairness definitions onto that setting. And finally, we are covering multidisciplinary work here. So this is not just work coming from social choice, but also a lot of work nowadays popping up in the machine learning literature that is taking those social choice ideas and then applying that in sometimes not so straightforward manner. So Evie and I have done our best to try to review all this literature and then to kind of summarize all this literature and put that into a consistent framework. That was our goal for this tutorial. But that means that sometimes we had to take the liberty to do some simplifications so that we can kind of put two settings, let's say side by side with a similar notation and then kind of similar settings. It also means that because we are not super familiar with this whole multidisciplinary literature, there might be some errors here and there. If you notice some of those errors either during the tutorial or afterwards, then please reach out to us. We would be very happy to correct them in future versions. All right, so let me, before talking about this kind of goal of applying social choice fairness definitions to AI and machine learning, let me talk a little bit about why we care about fairness. So as humans, we have always cared about fairness kind of going back to millennia. But nowadays, the fairness literature is really booming because of a lot of applications where automated decision-making is being deployed. So think of AI tools that are used for screening resumes of job applicants, or kind of algorithms that are deciding which ads you see when you go online and you interact with a website that has some of the ad slots, Or you have AI tools that are kind of deciding how a car should drive itself autonomously. And so some of these are very high stakes decisions. And when these decisions are made, different people or different groups of people, they are affected. And then these are just some example applications. There are lots and lots of other applications where these tools are now deployed. And because of these, people are starting to get worried about whether these different tools are making decisions in a manner that's fair to the different people or the different groups of people that these decisions affect. And because of this, in the kind of the last wave of AI that happened in the last wave of machine learning that happened starting in 2010, the fairness literature in machine learning has been exploding at an amazing rate. But I just want to highlight that this is just the tip of the iceberg. Behind this sits a vast amount of fairness literature coming from social choice theory that dates back to at least the 1950s, some of it even earlier than that. And a lot of this literature, in my personal and very subjective opinion, is much more mathematically rigorous and kind of comes with very strong provable fairness guarantees. And a lot of the more modern machine learning literature on fairness has also now turned to social choice theory and kind of is looking towards how to apply these ideas of fairness from social choice theory to machine learning problems, not just for fairness, but also for other problems like AI alignment. And so what we want to do in this tutorial is we want to kind of survey this area broadly defined as social choice for AI, applying social choice ideas to AI applications. And we are particularly going to focus on fairness. And nowadays, this literature in social choice on fairness is explored not just from the kind of the traditional economics field where social choice theory came from, but also in AI, theoretical computer science, and several other fields like political science and philosophy and psychology. And at a high level, social choice theory talks about aggregating individual preferences into good collective decisions. And what constitutes a good collective decision is kind of to the up to the eye of the beholder. So there is no one definition of what a good decision should look like. In fact, there is not even just one aspect in which we might want a decision to be good. Fairness is one such aspect, but you also might want the decision to be good in a variety of other ways. So that's kind of the broad landscape of social choice theory, but fairness has often been kind of the center point of defining what a good collective decision is when you have a decision that affects many different people at the same time. And so what we are going to do in this tutorial is we are going to first do a little bit of background on social choice theory. So we are going to see different fairness definitions that we are going to take from social choice theory and apply to AI and machine learning. And we are going to see them in an example setting in social choice theory. So this is to kind of, this serves two purposes. One is that you see the original background from which these definitions actually emerged. What are the settings in which people in social choice were thinking of these definitions kind of decades ago? And B, it builds intuition about why these are good definitions that we should care about in a very simplistic, stylistic setting. Once we have some intuition about what these definitions are doing, then we are going to take those definitions one by one, namely envy-freeness, Nash social welfare, and the core, and we are going to see how these definitions have been applied in kind of the more recent era in a variety of AI and machine learning applications such as classification, recommender systems, clustering, multi-amp bandits, rankings, federated learning, etc. All right. So without more delay, let me get into the background on fairness in social choice. And so I'm going to take this very simple setting as a running example. And this setting is that of allocating divisible resources. So some of you who might already be familiar with social choice theory might already know a lot about this setting. So please bear with me. I suspect that we may have other people in the audience and may have other people watching the recording later on who may not know this background. So I'm going to kind of go a little bit slowly and do a little bit of gentle introduction. So what we have in this setting is we have a set of agents. Now you can think of these agents as people, or you can think of these agents as kind of AI agents. It doesn't really matter. The one benefit of social choice theory is that the definitions that it proposes, these are broadly applicable, and they don't really distinguish between human agents and non-human agents. So you have a set of agents, capital N, and you have a set of divisible resources, capital M. So think of resources like milk, sugar, or a bag of rice, where if you wanted to take the amount of milk that you have and give a third of it to one agent or a fifth of it to one agent, you could do so. So you can split these resources as finely as you need to. And then we care about what it is that these agents want, because if we want to be fair to these agents, we need to understand what the agents want in the first place. Otherwise, it's really difficult to be fair to them. And so we are going to denote the preferences of each agent I using a utility function denoted as UI, which is going to place a value on every possible share of the resources that the agent can receive. And typically it is assumed that this utility function is additive linear. So this is the kind of the most stylistic assumption you can place, though people have also explored a lot of kind of other more general utility functions. But in this stylistic simple case, if you have a vector x, which is in 0, 1 to the power m, so the kind of the number xg denotes a fraction of good g in this bundle, then the utility that agent I places on this bundle is simply the sum over all the goods g. So this is the additive portion. The utility is additive across all the different goods g. And then you look at the utility that agent I has for the entire portion of that good G that's available and multiply that by the fraction of that good G that is contained in this bundle. And so this kind of linear increment of this utility in the fraction of this good that's being given to the agent is what this linear denotes over here. Right? So it's a very, very simple form of the utility function. You just kind of take each good, you multiply the fraction of the good that you'll be getting times your utility for the entire good, and then just add it up across all the goods. All right. Now, one thing I want to say here is that the literature in the fairness literature often distinguishes between the case of non-negative utilities, where all these utilities are 0 or higher, and the case of non-positive utilities, where all these utilities are 0 or lower, meaning that you actually have costs rather than utilities. And it turns out that these two settings, even though they seem symmetric to each other, they are very different, and they often result in very different guarantees. And typically, we have much stronger guarantees for the case of non-negative or positive utilities, and weaker guarantees for the case of costs, but that's not always true. And also for a lot of machine learning applications, cost version seems kind of more applicable just because machine learning literature started with the framework of loss minimization, where you have a loss function that you want to minimize. And so kind of this cost framework fits very nicely to that, but it doesn't always have to be the case. All right. So what do we want to do with this setting? We want to compute an allocation A, which is a matrix where the entry aij denotes the fraction of good g that is given to agent I. And because we want this allocation to be feasible, for every good g, if you take the sum over all the agents I, the fraction of that good given to the different agents, it should sum to at most 1. You cannot allocate more fraction than the total amount of the resource that's available. Note that I'm saying less than equal to 1, meaning that in an allocation, you can also throw some of the resources away. If you don't like that, you don't want to throw any resources, then you can talk about complete allocations where the sum is exactly equal to 1 for every good g. And now we can talk about the utility that each agent I gets under this allocation A as just the UI utility function of agent I, UI, applied to the ith row, AI, of this matrix, which denotes how much fraction of the different goods this agent I is being given. And so from this, you might think that we really only care about these n numbers, u1 of a1, u2 of a2, ... un of an, which is the utilities that the n different agents have under this allocation A. But that's not always true. A lot of the fairness definitions also use other interesting terms such as UI of AJ. How much utility would agent I have had if she were given agent J's allocation, right? So you kind of think about these hypotheticals and these counterfactuals, and sometimes the fairness definition relies on thinking about these. All right, so clearly we want to compute an allocation that's fair. What's fair? So let's look at some of the fairness definitions in this stylistic setting. So the simplest definition that was also defined the earliest, dating back to 1950s, is proportionality, which says the following. So you have, let's say, 3 agents, and you have these 3 divisible resources. So what you do is that a priori, if you assume these agents to be equally entitled, so no agent is entitled to a higher share of the resources than any other agent, which is true in many different settings, doesn't always have to be true. And in fact, there is a lot of modern research talking about kind of different entitlements. But in this tutorial, we are going to focus only on the case of equal entitlements, where everybody is equal and we want to treat everybody equally. So in this case, you can just take the resources that you have and divide them equally between the 3 agents and call these the entitlements of the agents. Okay, so each agent is entitled to an equal share of the green resource, an equal share of the yellow resource, and an equal share of the blue resource. Now, you could think of just doing this as the allocation, but that's not always a great idea if these agents actually have different preferences on which resources they want. For example, the guy over here might actually prefer more of the green resource, whereas the girls might prefer more of the yellow and the blue resources, right? So if that is the case, then you maybe want to give more of the green resources to the guy and more of the yellow and the blue resources to the girls in some proportions. So let's say you come up with an allocation that looks something like this, and now you want to check whether this allocation is fair. So what proportionality says is that this allocation shouldn't be any worse than the entitlements. Okay, but you have to be careful in defining what's worse, because these 3 different agents have 3 different viewpoints or perspectives on what's better and what's worse. So what we do more formally is we take the utility function of each agent. So in this case, let's take the guy over here. And so you apply the utility function of this guy to his own allocation and look at how much utility he's getting and compare that to his own utility function for his entitlement. Okay? And you make sure that he views his own allocation at least as good as his entitlement. And then the same has to hold for the other 2 agents in the system as well. And so each agent should personally view their own allocation at least as preferable as their entitlement. And if all these 3 inequalities hold, then we say that this allocation is proportional. All right, envy freeness is a little bit different than proportionality. Here, we don't really care about the entitlements. What we do care is how each agent views their own allocation versus the allocations of the other agents. So for example, if you look at the guy, he would compare his own allocation versus the allocation of this girl in the middle over here, and he wants to make sure that he views his allocation as at least as good as that of the girl. And he would do the same kind of comparison between his allocation and the allocation of the 3rd agent over here. And his allocation should be the best out of all 3. That's from his perspective. And the other 2 agents would do a similar kind of calculation and would have 2 inequalities for each of the other 2 agents as well. So in total, we will have 6 inequalities. And then when all of those 6 inequalities are satisfied, then we would say that this allocation is envy-free. And so more formally, the formal definitions look something like this. For proportionality, you would compare UI of AI. So this is the utility of agent I for the allocation given to agent I, and you would make sure that that's at least as much as the utility of agent I for her own share of the her own entitled share of the resources, which is just 1/n of all the resources, where n is the number of agent. Okay, so what you do is you take all the resources, divide by 3, and compute the agent's utility for that. But because we assume the utilities to be linear, you can actually take this 1/n factor outside, and you can say that this is 1/n of the agent's utility for all the resources combined. Okay, these 2 are going to be equivalent, only in this very simple setting. Envy freeness takes a different viewpoint. Here we look at agent I's utility for her own allocation versus agent I's utility for the allocation of another agent J. And we make sure that the former is greater than or equal to the latter for all I, j. So note that here I'm writing agent I shouldn't envy agent J, but when you apply it for all ij, it would also mean that agent J shouldn't envy agent I, and that inequality would have uj in it on both sides. All right, so just to make sure that we are all on the same page, here is a very simple question. What's the relation between these 2 notions of proportionality and envy freeness? Which means that if I take an arbitrary allocation A, which of the following has to always be true? First, if A is proportional, then A has to be NV-free. Second, if A is NV-free, then A has to be proportional. C, which is that both of these statements have to be always true, meaning that these two notions are actually equivalent. Or D, neither of these statements have to be always true, meaning that these two notions are actually incomparable. So take a moment to write down what your answer is, what your guess is for this question in the chat. So just write down A, B, C, or D on the chat. Any guesses as to which is the right answer? All right, there is a guess for B. Anyone wants to take a different guess? There is another guess for B. Right. There's a third guess for B. So I would say the unanimous consensus of this crowd is B. And this is an example where when you have a tricky question, the wisdom of the crowd can be wrong. The correct answer, at least as I've defined everything on the slides here, is D. And that's, I think the people who answered B have the right intuition, which is that in general, NV-freeness is a strictly stronger notion than proportionality. But note that I've asked this for an allocation, and I defined an allocation to be a potentially incomplete allocation where you can throw away some of the resources. And when that's allowed, NV-freeness doesn't necessarily imply proportionality. That's because, for example, if you have an empty allocation where you throw away all the resources, you don't give anyone anything, that's definitely NV-free. Nobody envies anyone else. But it's not proportional because everybody views their allocation as, which is the empty allocation, as being worse than their entitlement. Okay. Certainly, proportionality also doesn't imply NV-freeness. Proportionality just means that you get at least as much utility as 1/n of everything, which leaves n minus 1 over n of the resources being allocated to other agents. But a lot more than 1/n of everything could be allocated to some one particular other agent in your perspective. Yeah. All right, but the reason I say that the people who answered B had the right kind of intuition in mind is that if I just change the question slightly to add the word complete, so then for a complete allocation, it is indeed true that whenever A is NV-free, it implies that A has to be proportional as well. And if you want to see why, then you can just take the NV-freeness definition and you can average this over all the different values of J. The left-hand side would remain the same, and the right-hand side would average out to exactly 1/n of the utility of I for the entire set of resources. Okay, so this is something that you can very easily check. And in general, so NV-freeness is stronger because in general, we do want complete allocations. We don't want to unnecessarily throw away resources. All right, now let's briefly look at a different notion called the core. The idea behind the core is to take proportionality, which is a slightly weaker notion, and then boost it up to the level of groups of agents. So here we are going to consider every possible group of agent. And when we consider a particular group of agents, let's say the group of agents 2 and 3 over here, what this group can do is not just individually compare their own kind of allocations to their own entitlements, but they can actually take their entitlements and then redistribute it amongst themselves however they want. And then they can compare the allocations to the redistributed entitlements. So what that means is that when you consider a group like this, you can take these entitlements that these two different agents have and then redistribute them between these two agents however you want. Okay, and so let's say here is one particular redistribution, and now each agent would compare their own allocation to their redistributed share of their entitlement. And now the allocation shouldn't be a Pareto improvement over the new entitlements, meaning that it shouldn't be the case that every agent views the redistributed entitlement as being better than their own allocation. Okay, and so in the social choice terms, the redistributed entitlements shouldn't be so-called a strict Pareto improvement over the current allocation. Okay, not every agent should be happier under the redistributed entitlement than under the allocation. So here's the more formal definition of that, and I'm going to write down the same definition in two different ways. They are the same for this example setting, but for a lot of other settings that you'll see later in this tutorial, they actually differ quite significantly. So there is a resource scaling version where you say that there shouldn't be any group of agents. So note that this holds for every possible subset S of the set of agents N. If you look at their entitled share of the resources, which is how much, each agent is entitled 1/nth of the set of all resources. So collectively, this group is entitled size of S over size of N fraction of every single resource. So you take their collectively entitled share of the resources and you redistribute it among these agents using a different allocation. Let's call it B. So no group of agents S should be able to find any redistribution B of their collective entitlements such that that redistribution gives them a Pareto improvement, meaning that UI of BI would be more than UI of AI for all agents I in this group S. If this happens, then we call that a violation of the core. If this doesn't happen, note this negative quantifier in the very beginning. If this doesn't happen, then we say that our current allocation A is in the core. Right? So I'm calling this a resource scaling version because you are taking these resources M and then you are scaling those resources down before allowing this group to redistribute those resources. There's a utility scaling version where what you do is just a slight change. You don't scale the resources. You let this group of agents take the set of all resources and allocate it amongst themselves however they want. Now, of course, this is too strong. We can't just let a small group of agents take all the resources and allocate it amongst themselves, because if you do that, of course, they would be able to find a Pareto improvement. But then what we do is we make the requirement of a Pareto improvement much stronger. We ask that even after doing this redistribution, even if I scale their utilities down by a factor which is proportional to the size of the group, so size of the group divided by size of the set of all agents, even after that, it shouldn't remain a Pareto improvement. Okay? And these two versions are equivalent for our very stylistic examples that we have chosen because of the assumption of additive linear utilities. So when you have these linear utilities, whether you kind of take half of a resource or whether you take the full resource and then you scale your utility down to a factor half, it's the same thing. Okay? But in a lot of other settings, these two notions are going to be very different. Typically, the utility scaling version is going to be more generally defined. Okay, all you need to do is to define the agents and the utilities. The resource scaling version will only be defined if there is some way to scale some notion of a resource. Okay, so we are going to see a lot of different settings in this tutorial, and we are going to see what type of resource is it that we are really allocating and how to actually scale that resource down by a fraction that's the size of the group divided by the size of the population. Okay, so it's only defined whenever there is some sort of resource that you are allocating that you can scale down. But when it's defined, it actually ends up being a little bit more appealing in that particular application domain. All right, one last thing that we want to do for the background is look at the Nash social welfare definition. And here, this is the Nash social welfare of an allocation A is defined as the geometric mean of the agent utilities under that allocation. Why the geometric mean? It's not the only welfare function around. There are other welfare functions that are also quite popular, such as the utilitarian welfare, where you take the arithmetic mean, or the egalitarian welfare, where you take the minimum agent utility, which is kind of the L minus infinity mean. But the reason why Nash social welfare has gained a little bit more prominence when thinking about fairness is that in a lot of settings, optimizing the Nash social welfare yields a fair allocation, whereas optimizing the utilitarian or the egalitarian social welfare does not. And so in this very stylistic setting, it's very well known that any allocation maximizing the Nash social welfare is going to satisfy envy freeness and will be in the core. And this is kind of a provable fact, a provable fairness guarantee that you can give. Whereas if you optimize one of the other social welfare functions, then you wouldn't get this guarantee. And we also know that this such an allocation can be computed in strongly polynomial time, which is a great thing. Now, I'll just show one example application of core, this notion of the core to a different setting. And this will be a little bit more related to the kind of other settings that we'll see in the tutorial. This is still a social choice setting, not an AI machine learning setting, but it's a little bit closer to a lot of other settings we'll see. And so this is the setting of committee selection, where the setup is that you have a set of voters N, and you have a set of candidates M, and each agent I approves a subset of these candidates. So let's call this approval set AI. And then our goal is to choose a subset of the candidates. And when you do that, let's call it W, the utility that agent I gets from this collective decision W. So now note that we are no longer allocating a certain AI to agent I. There's just one decision W that we are choosing collectively. And when you do that, each agent simultaneously derives some utility from this collective decision W, which is just in this very simple case, just the number of candidates that we have chosen that agent I approves. Okay? And our goal is to find a subset of K candidates, so where K is a given number, that's fair. Okay, so somehow we want to trade off the different preferences that these different agents have in terms of their AIs, and we want to find a collective W that we want to choose. And here, for example, the resource scaling version. So what's the resource that we have here, which is K, the number of candidates that we are allowed to choose. So in the resource scaling version, what we would do is we would say that W is in the core. If there is no group of voters S and no subset of candidates T that this group can afford. Okay, so here we are going to scale this resource K down by a fraction that depends on the size of this group. So we are going to take K times the size of this group S divided by the size of the population N. And we are going to require that this group only choose a different subset of candidates that's at most this much in size. And then this new decision T shouldn't be a Pareto improvement for this group over the current decision W that we have chosen, where we have chosen actually K candidates. Okay, so it shouldn't be the case that UI of T should be more than UI of W for every I in S, where note that T is just choosing very few candidates that's proportional to the size of the group, whereas W is choosing K candidates. The famous open question in this particular setting is whether a committee in the core always exists, and a variety of approximation results have been known, but we are not going to get into that because our focus is on AI and machine learning. All right, let me just say one thing about certain advantages that this style of fairness notions hold over some of the other fairness notions that have been studied in machine learning, and then we'll dive right into the AI machine learning literature. So one advantage, in my opinion, is that these notions tend to be more broadly defined. All you have to do is define who the agents are in your application and what the utilities of those agents are for the different outcomes that can happen. And then suddenly you can take some of the definitions like the core and just apply that to your setting. Okay, and because of this, these same notions of NV-freeness and the core have been applied to many, many different settings simultaneously, whereas previously in a lot of kind of the traditional machine learning fairness literature, you take a setting and then you define fairness notions for that setting specifically. The other thing is that these notions kind of respect the preferences of the agents, which is kind of makes sense because these are the agents to whom we want to be fair. And how can we be fair to them if we don't know what they want? And as a consequence, kind of when you go beyond just binary decisions of whether to give something to the agents or not, you really need to kind of pay attention to the preferences. Okay, so these notions tend to be defined more broadly, even within one particular application area. And finally, notions like the core achieve group fairness to all possible groups. Okay, so note that in the definition of the core, we say all S that are subsets of N. So we don't have to pre-specify groups that are based on race or gender or only some of these very specific attributes or even the intersections of these attributes. It simultaneously gives a guarantee to every possible group, and the guarantee also scales automatically with respect to the size of the group and what the group can achieve cohesively without having to kind of set any subjective choices of free parameters. All right, so with that, let me dive into the kind of the second portion of this tutorial, which is looking at NV-freeness in machine learning. So first we are going to think about classification, where the basic setup is as follows. we have a population of individuals given by a distribution D over some kind of, let's say, Euclidean, high dimensional Euclidean space X, where each individual I is represented using a data point Xi, and a classifier F acts on this space X and then maps every point in this space to a classification outcome Y. Okay? And this can be several different types of classification outcomes. You can have a binary classification where this Y is just 0 or 1, so to give some positive treatment or not give it. Or you can have a hard multi-class classification where this Y is still discrete, but now has size more than 2. Or you can have a soft classification where now the Y is a continuous interpolation between the different classes. Okay? And so you can also think of this as a probability distribution over the different classes. And typically, in a lot of machine learning settings, other than the fairness consideration, you also have an objective that the principal is trying to optimize, which is typically represented as minimizing some sort of a loss function. So you write down the expected loss that you have for giving classification outcome f of x on data point x, as this x is drawn from the underlying distribution D that we care about. Yeah. And if f of x is a soft classification, meaning a probability distribution over different classes, then we just kind of, this loss for this soft classification is just the expected loss for the hard classification sampled from the distribution. But then we don't just care about the principal's objective, we also care about fairness to the agents, for which we need to know the utility functions of the agents. And here it's typical to write down just a single utility function that's defined as on the domain of x cross phi. So, so if you have, for example, if you want to find out the utility that agent I has for her own classification outcome, you can just call this global utility function u and input xi comma f of xi. Yeah. And then since we have these two different objectives, one is the principal's objective and then the other is some kind of fairness consideration, you cannot optimize both of them simultaneously. So a lot of this literature focuses on optimizing the principal's objective subject to the fairness written down as a constraint. All right. So let's focus on the first definition of fairness. This is the traditional definition of fairness that originated in machine learning. And then we are going to talk about how this relates to envy-freeness and some of its generalizations. This definition is called individual fairness. And the high-level idea is that if you have similar individuals, they should be treated similarly. Okay, so what you do is you take every pair of individual x and y, you look at their classification outcomes f of x and f of y, and you look at some form of a distance or discrepancy between these two classification outcomes, which is given by this function capital D. And you demand that this discrepancy between the classification outcomes that individuals x and y get should be less than or equal to the distance between these two individuals given by some underlying distance metric. So this distance metric has to be given to you. It's something that the application kind of designer chooses based on the domain knowledge. But then you can define this particular definition. So what's the kind of the pictorial idea of this fairness definition? Let's say you have these two students who are graduating, and they each want a kind of certain kinds of jobs, and they have similar CVs. So they have received kind of the same grades. They have had same kind of prior experiences, and if that's the case, then the probability with which they receive this job that they want should be roughly similar. Okay, so if these two are similar candidates, then the probability of being hired should be similar. So that's all fine and well, except when you have heterogeneous preferences. So now imagine that one of these users actually has a different preference. Okay, so she wants to go into academia, this other agent wants to go to industry. Now, what the individual fairness would demand is that the probability of each of these two agents receiving an academic job and the probability of each of these two users receiving an industry job should be the same. Okay, so let's say both agents receive an academic job with probability 0.3 and an industry job with probability 0.7. This would certainly be fair, but it's too restrictive. When these two agents have different preferences, it should be okay to give them different outcomes. And somehow we want to capture that. And envy-freeness says the following. So it's the primitive way of capturing this notion. It says that at least when you have equal individuals that are equally entitled, they shouldn't envy each other at all. So a classifier F is NV-free if for all X and Y, if the utility, now note that we are suddenly bringing in the utility, which is what a social choice notion would do. The utility of individual X for her own classification outcome should be greater than equal to the utility that individual X has for the classification outcome of any other individual Y. Okay. So this now allows giving this girl over here an academic job with high probability, whereas the guy over here an industry job with high probability, as long as the girl actually prefers her own classification outcome to that of the guy, and the guy prefers his own classification outcome to that of the girl. Okay. All right, but this own this was actually done. By the way, one thing that I did not mention is that whenever we are talking about any paper, the citation would be up there on the slide, below the title. I'm not going to talk about all the citations because talking about a lot of the different author names can be quite a mouthful. But the short citations are here, and the long citations will be at the end of the slides. So one observation here is that NV-freeness ends up being too strong for a deterministic classifier, which is that, so here is a simple example. Actually, you know what, in the interest of time, I'm going to skip this simple example. But all this is to say is that if you want to demand NV-freeness, deterministic classifiers are too restrictive and you should move to randomized classifiers. But let me move on to other fairness notions that you can define when you have individuals that are not equally entitled, but similarly entitled. So now let's bring back the idea of a distance function between two individuals, d of x comma y, but then demand that somehow these two agents should be treated similarly if the distance between them is not too much, but taking into account the preferences that these agents might have, which may be different. And so this notion of preference-informed individual fairness says the following, that if you take any pair of individuals X and Y, I'm not directly going to demand that the classification outcome of X and the classification outcome of Y be similar. Instead of that, what I'm going to say is that there should be some Z, some classification outcome that is not too different from the classification outcome of Y. So D of Z comma F of Y is at most the distance between X and Y. And agent X prefers her own outcome to at least that outcome Z. Okay. And so this now again allows us to give the academic position to the girl and the industry position to the guy, because the girl could just kind of take Z equal to F of Y, and that would certainly satisfy this definition. So it's a little bit more relaxed than that. You can also define a variety of ways of kind of, so in some sense, this is an approximate version of NV-freeness. You can also define approximate NV-freeness a bit more directly by, for example, just looking at the NV that agent X has for agent Y's classification outcome, and then limiting that to some epsilon, or limiting that to the distance that between the two individuals according to some metric. All right. In some settings, these individual level NV-freeness becomes too strong. For example, if you were to give out loans or bails, then individual NV-freeness is too strong because somebody who gets the loan will end up envying somebody who doesn't get the loan. Okay. So in these settings, we often care about fairness only at an average group level. So this is a notion that's actually weaker than the individual fairness notion. So what we say is that if you have two groups G1 and G2 that are equally entitled, then when you take an individual, a random individual from G1, or which is X, a random individual Y from G2, then on average, the NV that X has for Y should be less than or equal to 0. Okay, which means that on average, an individual from G1 shouldn't envy an individual from G2, even though certain individuals from G1 might envy certain individuals from G2. All right. The good thing is that you can actually impose this type of NV-freeness on average group level between many, many different pairs of groups, and you only need very few training samples for that. All right. So another nice thing is that this type of definition actually extends and captures some of the traditional machine learning fairness definitions like demographic parity, equal opportunity, or equalized odds, and actually extends them to non-binary decision making. So in the interest of time, I would also skip that since we are approaching the end of time. All right. Okay. So Here is another type of application of NV-freeness to different groups. So this is where you actually don't want a single classifier to be applied to the different groups, because these different groups actually require different treatments, which is common in medical contexts. So the basic idea is that you can train a separate classifier for each group. Okay, this would be great because it can give each group exactly what they want, except you often don't have a lot of data for some of the small intersectional groups. So the solution here is to collectively train a separate classifier for each group while satisfying some sort of fairness constraints. And this paper here looked at two different constraints. One is that the separate classifier that each group gets should be at least as good for that group as the overall classifier or the pooled classifier that you can train that applies to all the groups, which means that it actually ignores the group membership, as well as the separate classifier that each group gets should be preferable to that group at least as much as the classifier that any other group gets as well, which is the NV-freeness constraint. Okay, so for example, if you have these three groups that you care about, let's say young males, old males, and also just females, where you don't actually distinguish between young and old, perhaps because you don't have a lot of data, and then you train one classifier that globally, as well as one classifier for each of the three groups, and then each group should prefer their own classifier to both the global classifier as well as the classifier of any other group. Right? Okay. So, right. I believe Laura, I guess Laura is not here. Karina, I just wanted to ask how much flexibility we have in going a little bit over.
I think it's fine.
Okay. All right. So I'll just run a little bit over because I don't want to push kind of more content to Evie's portion. Okay, so I now want to talk about applying NV-freeness to the setting of recommender systems. Here you have a set of users and you have a set of products, and you have this recommender system sitting in between that decides which products will be recommended to which users. And so here is a basic model for this. You again have this individual represented by data points in some Euclidean space X. You have a set of items Y, and in this particular modeling, you have a set of context C. And a recommendation policy pi basically decides which recommendations to give to each user in which context. Okay, so for each user X, this pi X of Y given C would be the probability of recommending item Y to user X in context C. And then the utility function of this user will be the for the recommendations that this user is given is the expected over the context that this user can have, and the recommendations that can be given to this user in that context, the value that this user places on that recommendation in that context. Okay, so this value Vx is, think of it as just kind of the utility function for the individual recommendations. In this recommendation systems context, it is often called the relevance. And then NV-free, once you have defined your agents and you have, which are the users in this case, and you have defined your utility functions of these users for the different outcomes that can happen, which are the recommendations that these users can be given, then NV-freeness is very simple. It's the, you just say that for every pair of users X and X prime, the utility that user X has for her own kind of stochastic recommendations pi X should be at least as much as the utility of user X for the stochastic recommendations given to user X prime minus, let's say, some epsilon if you want to allow a little bit of flexibility. This is all great, except sometimes we also care about fairness, not just on the side of the users, but also on the side of the products, or rather really the producers. So let's say that these products are generated by different producers, when each producer is generating a set of products. Then we might also want that no producer is being treated very much unfairly compared to any other producer, which can be done in a couple of different ways. So there's one paper that looks at this as a many-to-many matching, where each user is recommended K products, and then each product can be recommended to a different number of users. And here the relevance of the products to users is again given by some kind of function V. You can define it on the domain X cross Y. And then the recommendation policy is again pi, and the pi X is the recommendations given to this user X, which are now deterministic, but up to a number of a total number K. And then in order to define, note that these recommendations might be different from the best K products that this user might want, because this wouldn't really be fair to the side of the products. And so in this case, we define the utility of a user X as the utility that they get under their current set of recommendations divided by the utility that they would have gotten if they were recommended their own personal best K products, the K products that they would have preferred the most to be recommended. And the utility to a product Y is just the number of users to which this product Y is recommended. And we want to somehow balance kind of fairness on both sides at the same time. And so fairness to the users here is captured in terms of envy freeness, but up to kind of one product. You exact envy freeness is not really always possible. So you say envy freeness up to 1, where you say that the utility of X for the recommendations of X is greater than or equal to the utility of X for the recommendations given to a different user X prime minus one particular item that they might be recommended, call this item Y. Okay. And for the product side, the fairness is in terms of making sure that each product is recommended to at least a minimum possible number of users, which is some E bar, some threshold that you set as the designer. And then there's one kind of result from this work that shows that there actually exists an efficient algorithm that achieves EF1 among all the users and any minimum exposure guarantee that feasible guarantee that you might be able to set among at least n minus k products at the same time. All right. Here is a different way to think about fairness on two sides. So you keep everything as is on the user side. Each user is recommended k products, except you don't really need this normalization here. So let's simplify that to just saying that the utility of the user is just the sum of the relevances of the k products that they are recommended. But then you also define the utility of a product Y as the sum of the relevances of all the users to which this product Y is recommended. Okay? And now, kind of the good thing about this is that we are not just counting the number of users, because we don't want one product to be recommended to 5 users, which are not really relevant for this product, and another product to be recommended to also to 5 users, which are highly relevant to this product. Okay, so it kind of takes that, kind of improves upon that utility function a little bit more. And now we can actually impose the same EF1 guarantee both on the sides of the users and on the side of the products. And one result from this work, which is actually my joint work with Evie, shows that when each side agrees on the ranking of the other side based on their relevance, then a policy that's EF1 always exists on EF1 on both sides. But this is an open question in the more general case. All right. Finally, let me talk about non-centroid clustering. So this is an application of envy freeness to clustering. So we are actually going to think about clustering in a bit more detail in Evie's portion when we think about the core, because we'll see that for the clustering application, core actually really builds in this idea of putting similar data points in the same cluster. Envy freeness doesn't do that quite as much, but because we are talking about envy freeness here, let me just cover that in my portion. So in the clustering setting, the goal is that you are given a set of data points and you want to divide them into k clusters. And it's called non-centroid because we don't really want to place any cluster center somewhere in this region. Okay, all we want to do is just partition the set of data points into k clusters. And we are going to denote this clustering C as kind of C1, C2, so on till Ck, which is a partition of the set of data points. So here is one kind of the nice clustering that you would want if these data points were to be clustered into 3 different groups. All right, so the basic model is that you have this set of agents N, you want to partition them into this clustering C, and the cluster containing agent I would be denoted by C of I, and you have a distance metric D on pairs of agents that's given to you, and this distance metric is used for defining the utilities that the agent, or rather the costs in this case, that the agents have for being part of a cluster. And in envy, so the utility is kind of the cost is going to be defined as the average distance to the other agents who are in that same cluster. And here, an envy freeness notion would say that my average cost, so if you look at agent I's cost for her own cluster, which is her average distance to the other members of her own cluster, which is what's denoted on the left-hand side here, should be at most as much as agent I's cost for any other cluster Cj, which is the average distance that agent I has to the members of CJ. Okay? Now, it turns out that an NV-free clustering like this doesn't always exist. So you need to approximate it, which is where you can kind of put in this approximation alpha, where you say that maybe this cost that agent I has for her own clustering is higher, but not kind of alpha times higher. Okay? And then the result from this these works is that and a constant approximation of NV freeness always exists. Avi and I also had a joint work where we actually studied a very similar setting, but with binary costs. So these were binary, and there we were able to derive an kind of a balanced partition where each cluster contains roughly n over k points, and the additive approximation of NV was less than n over k. So actually, if you kind of now divide it by the size of the clusters, then you would get kind of an additive little o of 1 factor, which could also be interesting. All right. Avi, I wonder if we might want to cover the NAS social welfare completely on your side then.